Okay, Ram, you are live now. Please start.
So hello everyone. So today is the second live session for Fourier analysis. If you have any such problems, just type it on live chat. Otherwise, yeah, I have started. Am I not audible? If you have no such doubts, then maybe I'll just recap about the convergence of Fourier series, how it works. I'll wait for next 5 minutes. Then I'll start just recapping the whole Fourier series and Fourier analysis, whatever is covered till chapter 5 and 6. If there are no any doubts, then maybe I'll just start recapping about the whole whole idea of convergence of Fourier series and this thing. So given any periodic, first of all, I start with Fourier series. So given any periodic function, we given any periodic function which is L1, which is in L1, it is integrable. What we do, we define quantities, coefficients an, bn, and a0 in some integral form. A0 is defined as integral of f over the interval, let's say minus pi to pi. An is defined integral of f with cos from minus pi to pi, and bn is defined integral of f sine from minus pi to pi. So in general, so I'm calling a function g of x is a naught plus an cos nx plus bn sin nx summation from n equal to 1 to infinity. So the concern is in what case the Fourier series will converge to function. One obvious case could have been that if function is continuous, but that's not the case. Just continuous will not actually help. So we need more stronger condition for the Fourier series to converge to function. Now convergence can take many forms. It can take pointwise form that you want, pointwise convergence, or convergence in some general norm, let's say L2 norm or L1 norm. So first of all, we need to define types of convergence also. So in the very first chapter, we try to, so first of all, first thing is clear that pointwise convergence is a very strong demand. So if a function is Holder continuous from say minus pi to pi, then we say that the Fourier series will converge to function pointwise. Or in some text, we will also see function is C1 smooth, then also function will converge pointwise, and the Fourier series will converge pointwise to a function. But there are other form of convergence also. For example, we know there is something called Cesaro convergence and Abel convergence. So if a sequence of numbers converge in normal sense, then it converges in Cesaro sense, but it's not the other way around. So Cesaro sense and Cesaro convergence is weaker than normal convergence, that is pointwise convergence. Abel convergence is even weaker than Cesaro convergence. So then we switch to Cesaro convergence and Abel convergence. In what condition the Fourier series converges in Cesaro sense, in what convergence it converges to Abel sense. So this will be covered in chapter, I guess, third and fourth. This is the next part of the convergence of Fourier series. Now what comes is Fourier analysis, Fourier transform. So till now we are dealing with function restricted to minus pi to pi. So now we try to periodic function restricted to minus pi to pi. Now what if we work with a general function? We want to define a similar kind of procedure. So again we start demanding first of all function should be in L1 of R. Let's say we are dealing with R1 only. So L1 function from L1 R. We defined a map called Fourier transform. That is f e to the power iota I chi x dx integral over whole R. This will give us something called f hat, which is called Fourier transform at eta. But if we try to apply the same analogy that we did for Fourier series, if we take the f hat times f hat multiplied by e to the power minus I x chi dx integral, it should somehow give us f back, but it doesn't in general. So we want somehow same kind of results for uh, general functions also. Then how do we do it? Later, for example, in chapter, I guess fourth or fifth, we have seen that if function is in L2, if a function is in L2, then the Fourier series of function converges to f in L2 sense. This we had seen for Fourier series. So we would expect something same like for Fourier transforms also. If function is in L2 of R, then somehow the Fourier transform should uh, we take the Fourier transform and just apply the same thing. We should also uh, give back the same function. Somewhat I'm just trying to push the same result that we did Fourier series to Fourier transforms. But here's the issue. It's not in general true. So now what we define is that we define something more generalized, not more generalized, specialized kind of function called function of Schwartz class. It has many properties. So I'll give you just three, four motivation why should we define Schwartz class. First of all, if you have a function and its derivative should, if you want derivative also to be, for example, if a function f is in L1, then we can take Fourier transform. If we want the derivative of the Fourier transform, the derivative of that function to be also to also take the Fourier transform, and the Fourier transform should be in L1, then what we want is that x times f at x times f should be x times f at x times f should be in L1. This should be our main goal. And if we want further more derivatives, we want some x to the power whatever derivative we want times f should be in L1. This is one of the prime motivation. Other prime motivation is that we want some kind of uh, set of functions for which we can take Fourier transform and we can apply some Fourier inversion theorem. All this will somehow lead to a Schwartz class, because Schwartz class is a property. You multiply with any polynomial to the function, you will get the new function will be of the same class. This is the property of Schwartz class. And Schwartz class is contained in L1 LP of R for all p strictly less than infinity and greater than 1. And uh, for function of Schwartz class, Fourier inversion theorem also holds, and its isometry in L2 sense also holds. And now we also know that function of Schwartz class is dense in L2. So if we have and we prove that this Fourier transform is continuous map from Schwartz class to Schwartz class, 1, 1 and 1, 2. Then from real analysis, we know that if we know that Schwartz class is dense in L2, then we can stretch this continuous map from Schwartz class to whole of L2. Therefore, we got the idea of how to generalize the Fourier transform for L2 functions. Now, what about L1 functions? So L1 function has some more subtleties. For example, even if f is in, we have to start with f should be in L1. Even if f hat is in L1, first of all, f hat need not be in L1. In what case, if f hat is in L1, in what case does Fourier inversion theorem holds? We have to prove it, and therefore we use a smoothing function e to the power minus epsilon x square. We multiply it, we apply dominated convergence theorem, and prove Fourier inversion theorem. Now, in between the slides, we have seen many important results like uh, writing Bessel's function in terms of integral of cos something, their manipulations. Then we had seen many problems like uh, minimizing parameter problem or heat equation problem. There are many problems that we have seen using Fourier analysis. So this was the whole crux of the content. Using Dirichlet kernel theorem, and we use Jacobi's identity, the Jacobi theta function identity, and using that we uh, for the Riemann theta function was not defined at 1. So using these identities, we gave us a method to generalize the Riemann theta function from C minus 1 to C. These were some main ideas of the this Fourier series and Fourier analysis, first 5, 6 chapters. I think live session has ended. There are no more queries. So I think technicians can close this session. Yes, sir. Yes, sir. We can close the session. There are no doubts. I have given a recap also, so I think we can close the session.
Thank you, sir, for closing this session. Thank you.